all, it's Sarah. We are moving on from derivatives into inverse functions. So today we're going to be talking about exponential and logarithmic functions. So first of all, I'm just going to define the exponential function. So it's a function of the form f of x equals a to the x power, where a is a positive constant. Now, we have some rules for exponential functions that I'm going to go through. So if we have positive constants a and b, and then real numbers x and y, then these rules are true. So a to the x plus y power is going to be equal to a to the x times a to the y. Our next rule is that a to the x minus y power is going to be equal to a to the x divided by a to the y. Next, a to the x in parentheses to the y power is equal to a to the x times y power. And then finally, a times b to the x power is equal to a to the x times b to the x. Now, we have this special number called e. So e, we're going to define it as the limit as x approaches 0 of 1 plus x to the 1 over x power. It's approximately 2.718. Now, we'll see in a little bit this is a very important number. It's so important that we actually define our natural exponential function using it. So our natural exponential function is going to have a base of e. So that's just e to the x. And this is going to be a continuous function. Its domain is all real numbers, and its range is from 0 to infinity. Next, we're going to talk about inverse functions. So a function is one-to-one or injective if for any x1 and x2 that are not equal to each other, we must have that f of x1 is not equal to f of x2. So what this means is that if you have two different numbers in the domain of the function, they will never map to the same output. Okay, so an inverse function, so basically a function is invertible if and only if it is one-to-one. And so if a function is one-to-one, then so like if f mapping from a to b is one-to-one, then we can define f inverse, which maps from b to a, and it's defined by f inverse of y equals x, means the same thing as f of x equals y. So that's the basic idea of inverse functions. In order to invert a function, the first thing that we're going to do is just switch x and y. And then we're going to solve for our new y. So then y is going to be equal to x minus 3 divided by 2. So that's how we invert a function. So the logarithmic function is the inverse of the exponential function. So log base a of x equals y means the same thing as a to the y equals x. So for all real numbers x, log base a of x equals x, right? They cancel. And then for all positive x, a to the log base a of x equals x. So in both ways, this is going to cancel. So basically, inverses undo each other. So some rules. X and y are positive. Then we have log base a of xy equals log base a of x plus log base A of y. That's our first rule. Our second rule has to do with division and subtraction. So basically these rules are kind of the opposite of the rules that we had with exponential functions, which makes sense because inverses undo each other. Our final rule is that for all real numbers r, log base A of x to the r power is going to be equal to r times log base A of x. So basically, we can move a power down from the argument to be multiplied to the logarithm. So the natural logarithm is defined similarly to the natural exponential function. So we write it as ln of x. What it means is log base e of x. And so what it means is ln of x equals y is the same thing as saying that e to the y equals x. Whenever we talk about logarithms, it's important to remember that they really are just exponents written backwards. They can seem kind of complicated on the surface, but if you just think of them as backwards exponents, they tend to make a lot more sense. The next thing we're going to go over is just the change of base formula. So if we have a positive number a that is not equal to 1, then log base a of x is equal to ln of x over ln of a. So basically, we can get any logarithm with any base to be in terms of a quotient of natural logarithms. Now we're going to go over the derivatives. So the derivative of log base a is going to be 1 over x times log base a of e, which we can also write as 1 over x times ln of a. All right. And then the derivative of ln of x is going to just be 1 over x. So we can kind of see why this might be a special case, right? And then the derivative of a to the x is going to be, well, just for a greater than 0, right? If a is positive, then the derivative is going to be a to the x times ln of a. Now, ln of e, since these undo each other, that's just going to be 1. So the derivative of e to the x is e to the x. Now that property is really, in the context of calculus, a big part of what makes e so special, is that it's the one number where when you plug it in as the a value in the exponential function, its derivative is itself, which is super useful in a lot of different applications. If you enjoyed this video, please like and subscribe, and I'll see you all next time.